Okay, it's 7 o'clock in China now. Hello everyone. Welcome to the 16th session of AsiaGraphics webinar. And I am Xuejin Chen from University of Science and Technology of China. It's my honor to chair today's session. And we are glad that we have two excellent speakers today. And we have two talks. The first talk is controllable generative models, the quest of photorealistics reloaded. And our first speaker is Professor Danny Lichsky, and I will give a short introduction of Professor Danny Lichsky. Danny Lichsky is a professor at the School of Computer Science and Engineering at the Hebrew University of Jerusalem, Israel. He received his PhD from Cornell University in 1994 and was a postdoc at the University of Washington until 1996. In 2002 and 2003, he spent a sabbatical year at Pixar Animation Studios. In 2012, he received the Eurographics Outstanding Technical Contributions Award. In 2017, he served as the technical paper chair of SIGGRAPH Asia in 2007. His research of interest span a wide variety of topics in the fields of computer graphics, image and video processing, and computer vision. Most of his recent work involves deep neural networks and their applications in graphics and vision. Okay, let's welcome Professor Danny Lichsky to give the first talk.
Thank you very much, Xuejin, for the introduction. Let me just share the screen for a second and start my presentation.
Just a reminder for our audience, if you have any question, and you can send your message through our live broadcast.
Great, so everybody can see my slides?
Yes.
Great, okay. So let's get started. So good evening, everyone. It's my pleasure to give the talk in this AsiaGraphics webinar. So today I'm going to talk about controllable generative models. Basically, over the last 10 years, my research agenda, as well as that of most of my colleagues, has changed drastically. And this extreme change results, of course, from the fact that deep neural networks have emerged and have been extremely successful in various tasks of computer vision and graphics and other fields as well. And of particular importance to people like me, who basically grew up doing computer graphics, starting from my master's thesis work and until now. It's the fact that today's generative neural networks, they provide like a whole world of opportunities compared to what was available to us just a few years ago. So in my talk today, I would like to first start with a very brief personal perspective and then share with you some details about a couple of my recent projects, all of which involve controlling generative models in order to synthesize and manipulate images. So I've been doing computer graphics for a very long time, like I said, actually since 1988. I'm pretty old. And I became fascinated with computer graphics after learning about ray tracing in a computer graphics course that I took. And then I ended up doing my thesis, my master's thesis on ray tracing. And this pink teapot that you see here is actually one of the images from my master's thesis. It's one of the first images I produced ever. And then I was so excited about photorealistic image synthesis that I went to pursue a PhD degree at Cornell University, which was the best place at the time for photorealism and global illumination. And there I work on radiosity. And here's an image from my PhD thesis over there. In fact, my advisor at Cornell, Don Greenberg, he was a big fan of photorealism, and we used to joke that he would like to start every paper with the words "photorealistic image synthesis is the holy grail of computer graphics." And in fact, I remember him adding this sentence to the beginning of one of my papers, but I removed it because I thought it was a little bit too commonly used. And back then, which was 30 years ago, we really didn't have any idea about neural networks, and we didn't even use optimization that much at the time. But already back then, we were really aware of the fact that ordinary image metrics, like just comparing pixel values, were not able to capture high-level concepts such as realism. And we were really talking amongst ourselves and fantasizing about developing some kind of a perceptual error metric or a photorealism oracle that would help us determine how realistic an image is and how its realism can be improved. And this is not a very simple task. For example, if I show you these two images, I mean, I cannot see you, so I'm not going to do a show of hands, but would you be able to easily tell which of those two images is real and which of those images is fake? Let's just take 5 seconds to think about it and form your own opinion. And in fact, both of these images are synthetic and they're fake. This just goes to show you that telling whether an image is real or not is not an easy task. But in machine learning, something has emerged that tries to address this task, which is the concept of discriminator in generative adversarial networks or GANs. So for those of you who are maybe not familiar with GANs, I will do a really short review. In 2014, there was a very famous paper published by Ian Goodfellow and several co-authors from the University of Montreal, which was called Generative Adversarial Nets. And they introduced a new kind of a generative model that was able to generate all sorts of data from different distributions, among them images that look like real images. So, since I was waiting for something like this for many years, I was very excited, and I was not the only one. Basically, you can see here on the slide that several famous people in the community have said that this is like one of the most influential ideas in machine learning in the last decade, and the number of papers that deal with GANs, and for example, just have GAN in their title or abstract, was growing very fast. And this plot only shows the growth of the number of publications only until 2019. It has continued since. I mean, nowadays there are other things people are very excited about, like transformers and diffusion models. We'll talk about some of them a bit later, but GANs are still very much play an important role in generative models. So the idea behind GANs, or generative adversarial networks, is to train a generative model by actually training two competing players. This is a concept that's called adversarial training, where one player is the so-called generator, which you can think of as a person who's trying to forge or produce fake works of art. But unlike an art forger in real life, the generator in a GAN does not really know what a real image looks like. So in that sense, he's working blindfolded and only receives some kind of a random vector as input. And the second player, which is part of the GAN, is the discriminator, which you can think of as a detective or an art expert, and whose expertise is to look at images and to tell whether the image is a genuine, original artwork or a fake work made by the forger. And the idea is to train these two networks or two models together, and both of them then are gradually improving until hopefully they reach some kind of an equilibrium, the Nash equilibrium. And at this point, the distribution of samples or images produced by the generator is really indistinguishable from the distribution of images in the training data. And then the discriminator, the best thing he can do is just to guess, just flip a coin to guess whether a given sample is real or fake. And in practice, both the generator and the discriminator are implemented as differential neural networks, and the training process just alternates between them while attempting to minimize some loss functions, which are written on the slides. I'm not going to go into the loss functions. That's a little bit outside of the scope. Okay. The discriminator, remember, is just a classifier whose goal is to classify samples as real or fake. And that's when he learns to classify them correctly, his loss decreases, and the generator attempts to increase the loss of the discriminator by producing samples which are indistinguishable from real ones. So that was generative adversarial networks just in a nutshell. And one of the major applications of GANs is synthesis of realistic images. And here we can see on this slide, we can see a demonstration of the progress of GANs since they were introduced in 2014 and until a few years ago, where I think they've reached pretty much the current level that they're at. This shows it on human faces, but GANs can generate other images, not only human faces. But basically, you can see that the degree of realism has been, and the resolution of the images that they can generate has been quickly increasing and improving. And in particular, this image on the right is generated by a particular GAN architecture, which is called Style GAN. It was developed at NVIDIA in 2018. And I'm going to talk about this architecture quite a bit in the next couple of projects that I'm going to be telling you about. So I just want to demonstrate to you that GANs and Style GAN in particular are not only good for generating human faces. So here you can see some examples of images of churches, images of bedrooms, and images of cars. They were all generated by different Style GAN models. So you need to understand that in order to generate an image from a certain class, you need to train a GAN model that specializes on that class. Okay, normally it's difficult to train a single GAN model that would generate just about any general natural images. Usually the images come from some restricted domain, but we'll have to live with that restriction for a while. Okay. So in order to explain to you something about the research that we've done on Style GAN, I need to explain first a little bit more about its architecture. Okay. So let's dive into the architecture of the Style GAN generator. So here on the left, what you see is the classical generator architecture, which is just a convolutional neural network with several stages where each stage increases the resolution further, and then you start with some image formed from a random vector, and you by repeatedly applying convolutions to it and increasing the resolution, you generate an image. Now the Style GAN architecture generator is a bit different in the sense that before it starts operating on the random vector, which we call the latent code, it first maps it into another space. So if the original latent codes, they're just some uniformly distributed or normally distributed random vectors, we have another latent space, which is called the intermediate latent space, and usually it's denoted by W. And there is a mapping function that maps the latent vectors from the simple space to this intermediate latent space. And then vectors from this intermediate latent space are further mapped using affine transformations into a set of style vectors, one style vector for each convolution layer. And these style vectors, their role is to modify the statistics of the activations inside each layer. And these different statistics are actually responsible for all the different images that the generator is able to generate. So what's extremely cool about StyleGAN is that this intermediate latent space, W, actually has a lot of rich semantic structure. And what's important about that is that the fact that we can take advantage of the semantic structure in order to achieve different changes to images simply by taking steps in the latent space. So for example, if we start from the original image, which you see in the column on the left, by taking steps in the latent space, we can generate images that look like they're older, or have all of a sudden have glasses, or look more masculine, or change the pose, and other types of changes like the illumination can appear differently, and or some of them repeat pose, expression, etc. So basically, the principle, just a second. Yeah, the principle is that each image generated by the StyleGAN is associated with some latent vector, let's call it W, and by taking some kind of a step, delta, in the latent space, we can get an image that is similar to the original image, but differs from it in some high-level semantic attribute. Okay, so there have been a lot of work, basically, that we're exploring and utilizing the semantics of the W latent space in order to achieve different types of edits and manipulations that you can do on images. Now, in that context, it's very important to mention this concept, which is called disentanglement. So what do I mean by disentanglement? Suppose we want to change the gray hair of the color of the hair of the person to become gray instead of black. Okay, but so the question is, when I do that, whether other attributes are changing as well. So for example, you can see here results produced by a couple of existing methods, and you see that while they managed to make the black hair to turn it into gray, they've also made the entire face look older, which may or may not be what we wanted. And another example is where we wanted to add some red lipstick to the face. And again, we can do that by taking a step in latent space. But in one of the existing methods, taking such a step also made the entire face appear brighter. And another existing method actually completely changed the identity of the person in the image. So those manipulations are what we would call entangled, in the sense that one change induces other changes. The changes are interrelated, they're entangled, they're not independent, okay? In contrast, what we would like to have for better user control over the result is disentangled manipulation, like the results that you have here, where only the change that you wanted to happen has occurred and nothing else has changed. Only the hair changed from black to gray, only the lipstick changed from natural to red, and nothing else in the face seems to have changed. Okay, so this is the this was the topic of the first project that I want to tell you about. This is a project with my PhD student who's since graduated. Actually, he's from China. His name is Wu Zhongde. And also with Eli Shechtman from Adobe. And that was presented in CVPR 2021. So basically, in a nutshell, what we try to do in this project is to answer two questions. The first question was, what's the latent space that's best to use for such types of disentangled semantic edits? And the second question is, once you decide which space to use, how do you find the direction in the space where you want to go, basically? So let's go back to the architecture of the style gun, and we can see that we actually have here sort of 3 or 4 different latent spaces. We have the original simple space Z. We have the intermediate space W, which sometimes people extended by creating multiple copies of it, and they call it W+. And also there's the space of these style parameters, which are the little boxes, the little blue boxes marked S1 through SN. So we found that in the literature, there are some measures that people have developed, or metrics that people have developed for measuring the amount of disentanglement of a representation. And what we found is that despite the fact that most existing works use either the Z space or the WW+ spaces to perform the edits, in fact, according to the standard metrics, the S space, which is the space of the parameters that modify the statistics of the convolution layers, is the one that has the best disentanglement characteristics. So we decided that we want to explore that space and to find controls within that space, to develop a methodology for finding the controls in that space that would allow us to create disentangled edits in images. Okay, so one part of that methodology uses the fact that we can create a semantic segmentation of an image. Like, for example, if we have a face, we can create a semantic mask that tells us where the hair, the nose, etc. are. And then we can examine the gradients of different style space components to see which of those components has a gradient with the greatest overlap with each semantic region. So, for example, we can find, for example, here we can find that the gradient of the parameter channel number 286 in level number 11 has a gradient which is very high at the areas of which correspond to hair, right? And so indeed, when we try to isolate the effect of this parameter, we see that indeed in this image, or in many other images, in fact, it changes the color of the hair from brown to gray and doesn't really do much else. Similarly, we were able to find that another parameter, maybe you should, I hope you can see here that the eyes of that person are changing their gaze, okay? And indeed, this parameter, which is parameter 409 in level number 9, it has a high gradient in the area of the eyes. And similarly, we were able to find parameters that control different motions of the mouth and different things that relate to other aspects of the human face, such as eyebrows, for example. Here's a bunch of other parameters that we found. They're all shown using the same face. So you can see we have a whole set of parameters that control different aspects of the hair, and quite a few parameters control different motions of the mouth, or things which are related to the eyes and the eyebrows. Okay, and each of them is just typically modifying just one attribute, one visual attribute, while everything else remains the same. You know, when we open and close the mouse, for example, the hair doesn't change, and so forth. So those are disentangled manipulations. And again, to convince you that this is not only helpful for faces, we also performed the same type of analysis on a style gun model that was trained on the set of bedrooms, Elsan bedrooms. And you can see we were able to find parameters that control the length of the bed spread, and whether or not there are pillows on the bed, and whether or not there's a lamp next to the bed, for example, while everything else is not changing. So that was one method with which we found how to discover semantically meaningful parameters in the space of the style parameters of style gun. So some attributes that we would also like to be able to control, they're not limited to a specific semantic area, or maybe they are, but we don't have semantic segmentations for them, for example. So let's suppose we want to find a control of the style gun which determines whether or not a person is going to be wearing a hat in the generated image. So we can pick just a few examples of images with hats, like, for example, of images of people with hats, for example, 20 or 30 such images. And we can compare their average, basically style vectors, to the average style vector over a much larger population of images, some of which may or may not have hats. You know, most of them were not going to have this hat because it's just one feature out of many. And then this way we can identify by performing this kind of like a signal to noise type of computation, which channel stands out in the exemplar images compared to the population of random images. And in this manner, we could also determine a large number of different attributes. Let me show you some examples. So, for example, indeed, we were able to find a channel that controls whether or not a person is wearing something on their head, whether or not a person, male or female, it doesn't matter, has a goatee beard, and also change the gender, the apparent gender of the person from appearing more feminine to appearing more masculine, without anything else changing. So, as you can see, operating in style space and seeking meaningful parameters in this way is a very powerful image editing tool. But everything I've showed you so far was done on synthetic images that were generated by the gun. They're not real images. Typically, what we would like to do is we would like to take a real image and to manipulate it. So, for example, suppose somebody gives this image of Will Smith, he's a Hollywood actor, and we would like to edit this image. So first, so this is a real image. It's not an image that's generated by a GAN. So the first thing we need to do is to invert the image, in the sense that we need to find a vector or a point in the latent space that generates an image that's maybe not identical, but very close to the image that we want to edit. And this is what an inversion might look like, is the image on the right. Okay. Now, once we have the latent code for this image, we can manipulate different style parameters, and we can make that image smile. We can add lipstick. We can change the gaze. We can do all these manipulations that we've discovered how to do on synthetic images, on real images as well. Here's another example. This is the actress, Emilia Clarke, and this is what her inverted, GAN inverted image looks like. Again, you can see it's not one-to-one identical, but it's pretty close. And again, we can perform all these edits that we've discovered how to do on generated images on real images as well. So that was a fun project that we've completed. But then the next thought was, well, it's a little bit tedious to look for through lots of controls and try to figure out what each control is doing. It would be much easier if we could just say what we want the edit to do and have that happen. So for example, we could take, if we could just take this image of the actor Leonardo DiCaprio and just say blonde hair, and then see this change happen, right? Or type angry and change the expression accordingly. Or change the hairstyle, for example. So that was the idea of the next project that I want to tell you about, which was in addition to Zhongde and Eli Shechtman. It was a joint project with Or Patashnik and Daniel Cohen-Or from Tel Aviv University. And here, the idea for this project emerged shortly after OpenAI released their CLIP model. CLIP is a model that analyzes images and texts and embeds them together in joint space. I will tell about how it works in a couple of slides. So the idea was to combine the power of CLIP and the generative power of StyleGAN together. So we created a system that was called StyleClip. So in order to tell you how StyleClip works, let's just briefly review what CLIP does. So basically, CLIP has two encoders inside it, which are trained using contrastive losses. And one encoder takes a sentence in natural language, and another encoder takes an image. And basically, they're trying to find embeddings for the text and for the image such that the embeddings are similar to each other using cosine distance. I mean, let's not go into the details of that, but basically that the embeddings are similar in this latent space of this CLIP model. So we use this idea to come up, the idea of combining CLIP with StyleGAN, and came up with 3 approaches. Due to lack of time, I will just tell you about one of them. That's the one that uses the same idea of utilizing controls in style space. So basically, given a text specifying some edit that we'd like to do. So suppose we would like to edit an image so that straight hair becomes curly hair. So for example, we can generate 2 sentences. One of them would be a woman with straight hair, another a woman with curly hair, and we could use the CLIP text encoding to embed both of them into the CLIP embedding space, and that would give us a direction in that space, right? So now we can try modifying lots of different channels in the style space, generate an image corresponding to a change in each channel, actually a pair of images before and after the change, and feed those 2 images through the CLIP image encoder, and we will get another direction in the CLIP embedding space. And this is for the manipulation of a single channel. So now we can take the dot product between these 2 vectors, and we can see how similar or how different they are. And if they're more similar than some threshold, we know that this channel is relevant to this edit that we would like to make. And basically, that would allow us to select this channel and to perform the desired edit by manipulating it. And we can select more than one channel. How many channels we select exactly is something that's called the disentanglement parameter. And as the disentanglement parameter increases, you can see the effects from the top row to the bottom row. The changes become basically more drastic. More things are changing, right? What in this example, what we would like to do is we would like to change the hair of Elon Musk from brown to gray. But if we allow the disentanglement parameter to take into account many different channels, then at the same time it makes Elon Musk older or younger, as you can see in the third row. Okay, so we've built basically, after analyzing the channels, which only takes like a couple of seconds, you basically can manipulate the image interactively. And here's a video that shows some of those manipulations. So for example, here, is it running? Yeah. So for example, when we type face with curly hair, the hair changed to curly. We type another style of hair, the style changes, and we can control the magnitude of the change interactively by the slider that we have. We can change the hair to be long or straight. And every time we enter a sentence like that, we analyze which channels are suitable for implementing this change, and then this change can be applied interactively. And maybe I'll skip to the next one. Yeah, so here's another example, I think, which is nice. So this is the inverted image of Boris Johnson when he was still a prime minister of the UK. And we can add some wrinkles to this face or remove the wrinkles, making his face appear younger. Change the expression to sad expression. And as you know, the opposite of sad is happy. So if we move the manipulation the other way, we get the effect of smiling. Change the gender to become more feminine or more masculine. And we can control how many parameters, how many different attributes are changing by controlling these disentanglement parameters. So if we decrease it, more things are changing, like the shape of the face and the hairstyle can change more drastically. So skip to the next example. Just to show again, not only on people, if we want to convert a car into a classic car, for example, this is what Clip knows about classic cars. It knows that they have the specific shape, or a sports car has this specific shape, and the Clip thinks that the opposite of a sports car is a minivan. And we can even make a cat cute by automatically, as you can see, using the style gun. Okay, here are a few more examples, but I'm gonna skip them in the interest of time because they basically repeat the same. So obviously, as a good researcher, you always have to try your own medicine on yourself. So when I try my own image and I gave it a text of a beautiful woman with gorgeous hair, this is what I got. So I don't know, beauty is in the eye of the beholder, so you'll be the judge of that, but it's certainly an interesting effect. So does this mean that we now can do whatever we want in terms of editing images? Not quite, because I've mentioned that GANs are very powerful, but they are domain specific. A special model needs to be trained to generate each domain. And when you want to operate on real images, you need to invert them first. And when you invert an image, as I've said, you don't get an exact image, only an approximation of it. For example, here you can see that if the image has some kind of a unique hairstyle, when you invert it into the gun space, that hairstyle can be lost. And the editing effects usually apply to the entire image. It's difficult to specify, I want only this part of the image to change, not that part. So we had another project, which I think in terms of time, I'm not having enough time to tell you about, but I will just mention it briefly, which uses, guns were very popular, but nowadays, basically most images are generated using diffusion models. And we've developed a method that allows a user to specify a mask on an image, like you see here in red, and to specify some kind of a text for the content that the user wants to have inside that area. And then the system generates the requested content. And like I said, we have been using diffusion models for that. So because of shortage of time, I'm going to skip the explanation of how diffusion models work. Again, we're using Clip, but I will have to skip all of that. I will just show you the results. So the methods we've developed, that was with another student of mine. His name is Omri Abrahami, and it was work presented in the last CVPR. Basically, the method we've developed allows you to remove images, like you see here. If we have this image of two dogs, we can draw a mask over one of them, and if we provide no prompt at all, this area just gets painted. Or we can provide some kind of a text over there and then have an object that kind of, according to Clip, is compatible with that text, like a ball of water, and so forth. Yeah, and this can be used to other purposes. For example, changing the background of a given image to be something else. For example, if we take a picture of a student sitting on the grass on our campus, but we can remove the trees in the background and make it as if the person is looking at a mountain or at something that looks like a Chinese. It's not really the Great Wall, but I mean, that's what Clip thinks is close enough to being something like it. Okay, so yeah, so again, in terms of what's left to be done, diffusion is very powerful, but the inference times, the time it takes to generate a single image, can be a little bit slow. And typically, furthermore, even though each image takes some time to generate, we need typically to generate multiple results because it's a stochastic process. It's a one-to-many process. We need to generate multiple results in order to be able to pick a single result, which is a good one. And also, language models like Clip, they have their own issues. For example, the Clip model is susceptible to so-called typographic attacks in the sense that if it sees a text inside some image instead of an object, it can think it's fine. So if we ask for a rubber toy in this image instead of the brown dog, it might generate just the text that looks like rubber, and Clip would think this is fine. Okay, so I think with this, I would like to end my talk because I think we're out of time. So I will just thank you for your attention, and all the codes for the projects I've mentioned are available on GitHub.
Okay, thank you. Thank you very much, Danny, for the nice talk. And Wait, I'm not sure. I didn't receive any questions from the audience now. And I want to ask you one question about the face generation. Actually, we also, in my group, we also did some work on sketch-based images synthesis. And one interesting application or task is to add some decoration items like eyeglass glasses or earrings, something like that. And well, I'm not sure if the problem of the GAN or the problem of the training data, when we edit these types of eye glasses or earrings, it seems that the model cannot model these types of things. Like when you invert the a real image into the latent space, it seems that the earrings or specific hairstyle is lost. Do you think it's the problem of limited training data, or just the capacity of the GAN model, because it seems that it only can model some synthesized
Right.
textures into some specific region, but it doesn't
Yes, yes,
know. Yeah.
yes. I think you're absolutely right. I think GANs are so good actually at generating a very varied collection of images because all this data is aligned, and you know, most people don't have these unique hairstyles or unique earrings, and so it learns to generate that, and it's not usually capable to generate very unique features. And like I showed in this image, indeed, if you have a specific style of hair, or he's also wearing some earrings. So and as you can see in the inversion, they're gone. Indeed, this is a problem, I think, with the GAN, because it tends to learn how to generate the more common modes in the distribution, and it tends to ignore the less common modes. And you know, there are many different types of earrings, and maybe each type appears only once at best in the data set. So in that case, it's difficult for a GAN to learn it. So you know what? But however, there are ways to achieve better inversion, which requires some fine tuning. So, for example, in the group of the Tel Aviv University from Dani Cohen-Or, there were several papers that proposed different kind of inversion mechanisms. And for example, one such inversion mechanism is called the pivotal tuning, the PTI. Basically, you start with a regular inversion, and then you fine tune the weights of the generator itself, the weights of the GAN, not just the coordinates of the latent space representation, in order to better capture the specific features of that particular image. Now, of course, you know, it's possible to capture such things to some extent, but you have to spend more computation time on that, because in addition to inverting, you also need to fine tune the model a bit.
Cool. Okay. Thank you again. Due to the time, I have to start the second talk. And thank you again. And for the audience, if you have any question, I think you can ask, send emails, or just let us know to send emails to Professor Dan.
Yes.
Okay. Thank you. Thank you very much.
Thank you very much as well. Thank you.
Okay. Then I will start our second talk. Okay, the second talk is given by Professor Ran Yi from Shanghai Jiao Tong University in China. And Ran Yi is currently an assistant professor with the Department of Computer Science and Engineering, Shanghai Jiao Tong University. She received the BE degree and the PhD degree from Tsinghua University, China, in 2016 and 2021. Her research interests include computer vision, computer graphics, and computational geometry. She has published over 30 papers in major international journals and conferences, and her talk is about audience-driven talking face video generation. Okay, I will stop my screen share and let Yiran to start her talk.
Okay, thank you, Professor Chen. And I will share my screen. So can you see my screen?
Yes.
Okay, thank you. So hello everyone, I'm Ran Yi from Shanghai Jiao Tong University. In this talk, I will present some works around audio-driven talking face video generation. And so audio-driven talking face generation is one research direction in the cross-modality learning of visual and auditory. And this task aims at transferring a speech signal into the visual information of a target person. So this task involves predicting lip movements, facial expression from speech, and also the head movements. It has many applications in digital human animation, virtual newsreader, and game generation, etc. And in this talk, I will present two works around this task. The first one is audio-driven realistic talking face generation. In this work, we focus on predicting personalized head movements from speech. And this video shows our results.
I needed a job. I wanted a job. I just had my second baby. My second son had just been born like 2 weeks before that.
And the second work is around audio-driven artistic talking face generation. And this paper aims at generating an artistic style talking face video, like of cartoon or line drawing or watercolor or painting. And the right side shows our results.
I needed a job.
Example,
I wanted a
we
job.
have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent. For example.
And next, I will first introduce the first work. So the title is Predicting Personalized Head Movements from a Short Video and Speech Signal. So natural head movements actually play a very important role in high quality communication. But most existing audio-driven talking face generation works, they use fixed head pose or head pose copied from another video. Some recent works predict head motion from audio, but they fail to address the one-to-many problem for the speech-to-head pose mapping. Actually, we noticed that the mapping from speech to head pose is a one-to-many mapping because there is some correlation between speech and head motion, but the coupling varies from utterance to utterance. This table shows a comparison with methods that predict head poses, but most of them don't consider the one-to-many mapping. Next, I will first briefly introduce some related works in this research direction. In talking face video generation, there is a branch that's the talking face video is driven by some source video. Like in this figure shows, there is a source person that is moving, is making some expressions, and the method aims at transfer the facial expressions in the source person or source video to a target person. And so video-driven methods can be categorized into two subclasses. One is based on traditional optimization, and the other is learning-based. And our task is audio-driven talking-based video generation. And the difference is that the facial expression is driven by a speech signal rather than a source video. And it is rather challenging because it involves two modalities. Audio-driven methods, they can be categorized based on the time span of the input visual information. Some methods use a single face photo to provide the visual information, and some use a short video, less than 15 seconds. Like our method use the second, it can be categorized into second category. And some use 2 to 3 minutes video, and some use very long video, like over 10 hours video to provide visual information. And also some method doesn't constrain the time span of the visual information. In our method, we also use the 3D face reconstruction as a model, as a submodule, because if we want to generate head movement, large head movements, we need to first use 3D face reconstruction to extract the head movements from some videos as the training data. And 3D, we use this 3D face reconstruction method based on 3D And 3D face reconstruction methods also can be categorized into two subclasses. One is traditional method and one is learning-based. We use the second subclass. Next, I'll introduce our method. So the target is to predict head movements from speech. We actually did some investigation in the correlation between speech and head motion, and we found some related works. So from the first related work, one of its conclusion is that there is a weak correlation between speech and head movements. And the second related work, and it has a conclusion that the coupling manner between speech and head motion changes from utterance to utterance. So the speech to head motion mapping is a one-to-many mapping. And from the second related work, we assume that a basic utterance unit only corresponds to one head movement pattern, and we assume a basic utterance unit ranges from a few seconds to a dozen seconds. That is often corresponds to a short video of 10 to 15 seconds. From these observations, we define the motion behavior pattern. We characterize the head motion in each short video, that is of 10 to 15 seconds, by a motion behavior pattern. And we think that different people will have different motion behavior patterns. And for one person, there are different motion behavior patterns in the different short videos of that person. And these two videos shows an example. These two videos are of the same identity, but they have different head motion patterns. Yeah.
Hello, I'm Emma from English. In this video, we're going to talk about 4 things that you can do every day to improve your English.
So the first short video of this person only have some slides, head motion.
You want to sound more natural, more casual, more like a native English speaker, right? Some of you also like my not so Australian accent, and you want to practice speaking like me.
And the second short video of this person has much larger head movements. So we think that even if for one person, he or she can have multiple head motion behavior patterns in multiple short videos. And we think that a short video of 10 to 15 seconds only corresponds to one motion behavior pattern. And in this way, so we can define a motion behavior pattern for each short video. And then if we have the motion behavior pattern, we can predict the head motion from speech signal conditioned on this behavior pattern. And next, I'll introduce how we extract the motion behavior pattern and how we conduct the mapping.
Hello, I'm Emma.
And we represent the motion behavior pattern as a vector in a feature space. And we extract the motion behavior pattern from a short video by 2 steps. The first step is to get the head pose sequence from a short video. And to get the head pose sequence, we use some 3D face reconstruction method. And the second step is to map the head pose sequence into a vector in the feature space. And we use an LSTM-based network to conduct the mapping. And to train the mapping, we conduct a data set containing different styles of head motions. And after we have extracted the head motion behavior pattern, we model the speech to head motion mapping as a one-to-many mapping as this function FAX. Here, A is the auditory feature extracted from a speech signal, and the X is a motion behavior pattern extracted before. And we map the A and X to a predicted pose sequence Y. And since we have this one-to-many mapping, given a fixed speech signal, we actually can change the motion behavior pattern X, so that using this function F, we can get different predicted head motion sequences, so that one speech signal can actually correspond to different head motions using this mapping. Now that we have 2 mappings, one is to extract the head motion behavior pattern, and the other is to predict the head motion. We design 2 networks for these 2 mapping. We design a head motion encoder, EM, for the first mapping, and design a head motion decoder, DM, for the second mapping. And here are the training losses we used to train these 2 networks. So after we proposed this head motion encoder and head motion decoder for the head motion prediction, we then proposed a talking face video generation system based on the head motion prediction model. Our talking face video generation systems can be summarized into 2 stages. The first stage is the stage 1, actually maps from audiovisual information to 3D facial animation. And the second is stage 2. It maps from 3D facial animation to realistic talking face video generation. I will introduce each stage in detail. So stage 1 actually consists of 3 models. The first one is 3D face reconstruction based on 3D MM, and the other is and the second is audio to expression mapping, and third is from the audio and head pose sequence to predicted head motion. So the first one, for the 3D face reconstruction, we use an off-the-shelf 3D face reconstruction network, which reconstructs 5 components from a face photo. The components can be categorized into shape, texture, lighting, expression, and pose. And the second module for the stage 1 is the audio to expression mapping network, and its input is some audio features, and its output is facial expression coefficients. We design an LSTM network to establish mapping. And the third model in the stage 1 is we previously introduced the multimodal input to head pose mapping, we actually just use the head motion encoder and head motion decoder to conduct a two-step mapping. And the second stage is from 3D facial animation to realistic talking face video generation. It also consists of three models. The first one is a rendering model, and the second one is the background matching, and the third one is a GAN model to refine the rendered frames. So in the first model, the rendering model, we actually combine the expression and head pose predicted before with the 3D reconstructed identity, texture, and lighting, and combine these 3D MM coefficients and render them into a video sequence. And second model is a background matching, because the rendered frame does not have any background, so we use the background in the input short video to match the background with the rendered image. We first match for the key frames which have the most critical head movements, and then we interpolate for the frames in between to neighboring key frames. And after that, we use a GAN to refine the rendered frames. We have use a generator based on attention mechanism and use a discriminator to discriminate the result is good or bad. So for the generator, we use an attention mechanism that's aside from output the color mask, it also outputs an attention mask, and the attention mask attends to regions that need to be changed. And the color mask learns the realistic textures. And the discriminator, we adopt a very classical patch GAN network. And here we show some results. We first compare our method with state-of-art audio-driven talking face generation methods. The left shows some qualitative comparison, and we also have a demo video comparison.
I want people to know that you do not have to accept the box that society puts you in. Reinvent yourself the way that you want to. I want people to know that you do not have to accept the box.
So in this,
puts
result,
you in.
we actually use a quite
Reinvent
slow
yourself
audio,
the way that you want
the comparison method,
Let's get started with two example words. The first example word that I have for you is ban.
So the comparison methods all copy the head motion from another video. So the head motion does not correspond that well to the input audio. So when the input audio is very slow, the head motion is still very quick, so that it's not very good. But we predict the head motion from speech and the head motion behavior pattern, so we can better generate the head motion. And here are some quantitative comparison. We use several metrics and user study to validate our results. And here is a video showing the pose variety.
Clip, I'm going to tell you the
weird and winding story of
two different
how I
audios.
went from
skeptic to daily
you do not have to accept
It all started with a
the
panic attack on
box.
national television. Clip, I'm going to tell you the weird
I
and winding
want
story
people
of how
to
I went
know
from ardent
that
skeptic to daily
you do
and
not
public
have
meditator.
to accept
It all started with a
the
panic attack on
box.
national television. Clip, I'm going to tell you the weird
I
and winding
want
story
people
of how
to
I went
know
from ardent
that
skeptic to daily
you do
and
not
public meditator.
have to accept
It all started with a
the
panic attack
box.
on national television.
Since the comparison methods all copy the head motion from another video, so given two different audios, they have the same they have the same head motion, but we predict the head motions. So for different input audios, we can generate different head motions. And here is another video comparison with the ground truth.
I needed a job. I wanted a job. I just had my second baby. My second son had just been born like 2 weeks before that.
I think that there are a couple of things. One, there is actually a hunger for different ideas, the monolithic nature of the.
I want people to know that you do not have to accept the box that society puts you in.
And this shows that given the same speech signal that we condition on different head motion behavior pattern, we can generate different head motions. And next is an ablation study to show the effectiveness of each module. And here is another ablation study result.
2 miles northeast, then 5 miles southwest, that sort of thing.
This verifies our head motion estimation. And here is a brief conclusion. So in this work, we propose a two-step mapping based on head motion behavior to predict personalized head pose from multimodal input. And based on this mapping, we propose the talking face video generation, which generates high quality talking head videos. And next, I will present the second work that is animating portrait line drawings from a single face photo and speech signal. Different from previous work, this work concentrates on artistic style talking face video generation. And this work is published on SIGGRAPH 2022 conference track. And so different from the realistic talking face video generation, artistic style, it can invoke different human experiences and leading to stronger visual effects. And it can enable new interaction and entertainment applications. And this figure shows our inputs and output. We actually have tried several artistic styles. Here shows a line drawing and cartoon. We also have tried watercolor and painting styles. And so for this task, there are not very much work in this specific research task. Some methods can conduct the photo to artistic portrait drawing style transfer, but they only deal with a static line drawing generation of static cartoon, and there are some video style transfer, but they require the input is also video, but they cannot generate artistic video from a single face photo and speech signal. And for the audio-driven talking face generation, the main methods they focus on realistic generation, like the previous work. And here shows a realistic generation. SIGGRAPH is one of the most highly respected venues for the presentation of new computer graphics technology and research. But these works did not consider the artistic style talking face video generation. So our task is different from the previous works. So the inputs is a single face photo and speech signal, and outputs is an artistic talking portrait drawing video like this.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
And this task, it requires two subtasks. One is the facial changes according to the speech, and the other is style transfer. There are no previous works to address this task, and we actually can combine some existing works to as a simple baseline. The first combination is that we concatenate realistic talking face generation methods and then conduct video style transfer on that. But that causes interframe discontinuity problems like this.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
The other way is to combine some static stylization method and then warp the stylized output to generate an animation, but that will cause unnatural and fake when under large head movements like this video shows.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
So these combinations, they both cannot generate very good results.
For example,
so to solve this problem, we propose a new feature warping framework to generate artistic and expressive talking, audio-driven talking face video. And we conduct both geometry change and artistic style transfer using a single GAN model, learning from static portrait drawing data, and ensure temporally coherent animation via two new coherent source terms. And we also propose a scheme to separate the processing of foreground and background to avoid inappropriate background warping. Our framework can be categorized into two stages. The first stage is to predict facial landmark from the speech. So in this framework, we use the facial landmarks as an intermediate representation. We first translate the speech to the facial landmark movements, and then to generate a new artistic video based on the predicted landmark sequence. And for the audio to landmark translation, we actually use a Make It Talk. We use the audio translation model from Make It Talk, and this network contains two branches: one speaker agnostic branch and one speaker related branch. We mainly focus on the second stage, which is the talking portrait drawing generation from the landmarks and the face photo. In this stage, we have to solve two challenges. The first challenge is to simultaneous style transfer and facial geometry change. And the second challenge is how to ensure temporal coherence from unpaired static data. To solve this first challenge, we propose a new generator based on feature level warping. We conduct warping on in the feature space to align the face image features to the target geometry. We warp the image feature according to some predicted flow map, and then apply the feature warping on multiple scales. So this feature level warping helps us to align the source geometry to the target geometry. And to cope with the generator, we also designed two discriminators. The first is a drawing discriminator, which discriminates whether the generated result is a good artistic style drawing or not. It contains a global discriminator and 3 local discriminators for important facial features. We also designed a temporal coherence discriminator, which discriminates whether two joints are temporally coherent or not. And this network is only used for line drawing style where we use a color portrait film and extract the lines as an approximate data for the line drawing. And for the other styles like cartoon or watercolor, since we don't have the real examples, we don't use this network. And for the loss functions, we designed 6 loss terms. The first 4 loss terms are used to solve the first challenge, that is to simultaneous conduct style transfer and facial geometry changes. It consists of an adversarial loss for GAN and a warping-based content loss, and also a geometry loss based on landmark detector and an identity preservation loss. The last 2 losses are designed for to ensure temporal coherence. The first temporal coherence loss is based on interframe warping. We generate 2 drawings conditioned on 2 target landmarks, which have slight changes. And we warp the first generated drawing to the second target landmarks. And we constrain that the warped results should be similar to the second generated drawing. So this warping-based interframe loss can help ensure the temporal coherence, since adjacent frames often have very small changes in the facial expressions. And the second temporal coherence loss is based on the coherence discriminator, and this is only used for line drawing style. And for the discriminator, it needs real samples and fake samples, since we only have unpaired static data. So we generate some approximate data as the real samples. We use a color portrait film and extract the lines of it. And we take the extracted lines of adjacent frames as the approximate real samples, and the extracted lines of non-adjacent frames as the fixed examples. And also the generated drawings conditioned onto slightly changed target landmarks are also considered as fixed samples. And apart from the architecture and loss terms, we also design a foreground-background separation strategy. This is used to avoid undesirable background warping effects. We can show it in this demo video.
And I don't know when your moment was.
Here is a teacher in front of a blackboard, and there are some text on the blackboard. That's when she speaks, the blackboard should not move, and also the text on the blackboard should not move. But if we do not use the foreground-background separation, the background will warp with the foreground.
But I bet you there was one.
This example shows.
But I bet you there was one.
So we separate the foreground and background processing to avoid this background warping effects. So we first conduct foreground extraction, and we generate foreground drawing using our proposed generator. And then for the background drawing, we use some static generation methods to make the background does not move. And then we blend the foreground and background results together. Next, we show some experiment results. First, this page shows some training data. So for line drawings, we mostly use the artistic portrait line drawings we collected from some websites. And these are only contain static drawings and unpaired data. And to train the temporal coherence discriminator, we extract some line drawings from a color portrait film and get these results. It can be seen that the extracted line drawings are very different in style from the data we collected from websites. So it is only an approximated data, but not very exact. And for the cartoon style, we only use the static data and does not use any video data. Here shows some comparison with baselines. For baselines, we actually combine several methods together, like here ATVG and SDA are some realistic talking face video generation methods, and UPD is a line drawing stylization method. So we compare our methods with these combinations.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent. For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
And we also compare with other baselines.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
And I don't know when your moment was, but I bet you there was one.
For example.
And I don't know when your moment was, but I bet you there was one. And I don't know when your moment was, but I bet you there was one.
And here are some quantitative comparisons. We conduct a use study and also use 3 metrics to compare with the baseline methods. And here shows results on other styles containing cartoon, painting, and watercolor.
And I don't know when your moment was, but I bet you there was one. And I don't know when your moment was, but I bet you there was one. And I don't know when your moment was, but I bet you there was one.
And so a brief summary, in the second work, we proposed a novel feature working framework to generate an expressive artistic talking face video from a single face photo and a speak signal. And we firstly proposed the method for the line drawing style, but then we extend the method to other styles, including cartoon, watercolor, and painting, and generate high quality results. And we also make the code open source. You can visit this GitHub page to try the code. And that's all for the talk. Thank you.
Thank you very much, Yiren. Very nice work. And I'm not sure. Any questions from the audience? Well, I want to ask you a question about your first work. And I see that you generated the face part according to the 3D model to synthesize the animation of the face region. But how about the hair regions? It seems that, I mean, you have a mask for the hair area, but how it is related to the pose?
Okay, I will show the screen again. So actually, in our framework, we consider the hair as a part of the background. So actually, when we match we conduct background matching, we will match the rendered face with the background that has the most similar head poses. So when we do the background matching, we will find a background with the most similar head pose with this rendering, so that the hair will cope with the face.
Consistent with the 3D face pose, right?
Yeah, right.
Okay, good. Have you ever applied your second work to the 3D animation?
we haven't applied that because in the first one we used 3D face, but the second we didn't use 3D. So in the second
the second one, yeah, the second one doesn't have the 3D post.
Yeah, yeah, but I think yeah, it can also use 3D in this in this framework. We can change the audio translation model and maybe change the condition to a 3D face components. Yeah.
Yeah. Another question about your first work, and it's in order to represent the motion behavior, it seems that you say map the motion behavior into a vector, just a vector, right? Is it related to the length of the video, or you use fixed length of the video to map several frames into a fixed dimensional vector?
Yeah, actually, we think each short video corresponds to one motion behavior pattern, and we actually constrain the short video to 10 to 15 seconds.
Okay,
Yes.
so you use fixed length. You just segment a long video sequence into several segments, pieces, right?
Yeah, right.
Thank you.
Thank you.
I think I didn't have any question from the audience, and now the perfect timing. And thank you again. Thanks our two speakers for their excellent talk, and thank you the audience for stay late to join us for today's seminar. Okay, and thank you again. And today we will stop here.
Thank you, Professor Chen.
Thank you. Bye.
Bye.